this video, we are going to begin our discussion of section 5.2, base 2 and base E. Obviously, when you check our first objective for today, we want to take a look at the similarities between some base 2 and base E exponentials. And in this video, we will also go over the doubling time model and the half-life model. We'll see where they come from, and we'll do several examples on how to use them. Thus, let's start here. Get your calculator and graph y equals 2 to the x, and also graph y equals e to the x. A couple of observations we need to make. Here I have e to the x and 2 to the x. The window I've chosen to use goes from -4 to +4, and from 0 to 20 on the y scale. Thus, when we graph them, we'll take a look and see here in the blue is e to the x. Here in the red, we have 2 to the x. And let's start by making a couple of observations about them. What do they have in common? Well, besides the basic exponential shape, you notice they do have another point in common right here. At the x value of 0, they both have a y value of 1. We can see some other differences that on the right-hand side, e to the x is growing at a faster rate than 2 to the x. Well, it may be a little bit tough to see. That's why I want to go into the table feature. Remember, table is accessed above the graph. So we go second graph to access the table. And we can see several values here. Here are a couple of things I would like to point out. Looking at 2 to the x, notice the pattern. For x of 0 to 1, we'd have 1, 2, 4, 8, 16, 32, 64. What's going on? Yeah, for each time, it's doubling. And it's perhaps a little bit harder to see, but if we go over to e to the x, we have 1, 2.7183. And then when we go to the second one, we have 7.3891, 20.086, and frankly, a lot of these things aren't really seeing them, but remember where they come from. We would have e to the 1 power is approximately 2.718. If we then multiplied that by another e, we get e squared and e cubed, followed by e to the 4th and e to the 5th. Keep in mind, each one of these stages, 1, 2, 3, 4, 5, for the inputs, are marching us forward, multiplying by the value. Once again, it's easier to see what's going on with y equals 2 to the x. Every time we move 1 forward from 0 to 1, we double. From 1 to 2, we double. 2 to 3 gets doubled. Each time we move forward, it doubles, which of course should happen with base 2. Well, when we were looking at each one of these things, and we had e to the x starting off at 1. As we were moving forward, 1 unit at a time, we saw at 1, it went to 2.7. When we had 2, 2.7 times 2.7 led us to 7.3. And so we'd have 1, 2, 3, 4, 5, 6, 7, 7.3. And by the time we had the third one, it was already off the charts up at 20. But we see how this form stacked upon itself. From 1 doubling to 2, doubling to 4, doubling to 8, and continuing upward, we saw how it got built. The behavior of them is the same, even though the bases are different. Once again, this should not surprise us. It's an exponential. All exponentials have this same behavior, or at least some variation of this behavior. But when we looked at the 2 to the x, that actually helps us lead to the doubling time model. How long does it take for something to double in its amount? Well, in this particular one, please notice how similar this is to what we just had with 2 to the x, the base 2 exponential. We saw that if this x were 1, and 2, and 3, and 4, each time it doubled. Well, instead of using x of 1, 2, 3, 4, let's consider times. A time of 1, a time of 2, a time of 3, and a time of 4. If we had a time of 1 over d, that's not going to double. What would the time have to be so that this were the fraction 1? It would have to be d over d. So if we have a time of d, we can have a double. Same thing, if we wanted this to be time over doubling time, to be the total fraction of 2, well, if we have t over d equal to 2, time would have to be 2 times d. The point I'm trying to make here, with the doubling time model, I'm not going to have the graph based on 1, 2, 3, 4. We're not going to have this counting 0, 1, 2, 3, 4, 5 on the bottom. Instead, our tick marks, instead of counting by ones, we want to count by the doubling time. 1d, 2d, 3d, 4d, and 5d. So if we started with an initial population right here at p of 0, at the doubling time later, it's going to be twice as high. So at 1 doubling time later, we are now here. Basically then a height of 2. The next time it doubles, at 2d, we're up to 4. At 3d, 4 would double upward to 8. This is the mathematical equation we will use to govern this behavior. Thus, I want to emphasize, for your notes, you will definitely want to have the formula written down. You will need it. Of course, since you're using the formula, you need to understand what each component is. P of t is the population at some time, typically off in the future. P of 0 is your initial population. Whenever you start measuring time of 0, that's what we're looking at. T is going to be the argument. It's going to play the role of our x whenever we do any kind of graphing. And d is some parameter. Just how long does it take for a population to double in its amount? You know, what I just, after changing over the page, I've redrawn the graph that we just had. In order to have a proper understanding of the doubling time model, this is a graph that should be memorized. Please notice where it came from. We have the initial population at p of 0. However high or down the x-axis, that's what we have. My scale then is not counting 1, 2, 3, 4. It's counting initial population, double, triple, quadruple, quintuple, and so forth. So it could be counting 10, 20, 30, 40, 50 if my initial population is 10. It could be counting with an initial population of 600. These tick marks could be 600, 1200, 1800, 2400, 3000. And please notice 0, 1 times the doubling, 2 times the doubling, 3 times the doubling, 4 times, and 5 times. So if my doubling time is 6 months, these horizontal tick marks are not 1 year, 2 year, 3 year, 4 year. It's 6 months, 12 months, 18 months, 24, 30. This is a model that should be memorized so that you have a proper understanding of the doubling time model. Now let's see how to use it. Remember what the doubling time model is. Can you write it down or do you have it for your notes? The population at some time in the future is given by the initial population to start with, and then we will multiply by a factor that keeps track of how many times does it double. That doubling factor is time over doubling time. Let's start putting the pieces in. A bacterial population is initially 10,000. Where does 10,000 go? That's the P of 0. The population at a time of 0. That's what we initially had. It doubles every 20 minutes. Well, where does that go? That's the D. Doubling time is the D. Give the growth model and the graph. Well, this is our growth model. The population at some time in the future is going to depend on that argument of how far into the future we want to look. This piece in the purple is the growth model. Now let's create the graph. That graph is based completely on this. Please notice, 0, doubling time, 2 times the doubling time. Each tick mark is going to march forward, just paying attention to 20 minutes for our doubling time, and then do another 20 minutes, another 20 minutes, another 20 minutes, another 20 minutes, and we could keep going farther and farther and farther, 20 minutes stacking on top of each other. Our initial population at time of 0, we had a population of 10,000. 20 minutes later, that population has doubled to 20,000. After another 20 minutes, it's doubled again, not up to 30, but when you double 20, you're at 40,000. When it doubles again, 50, 60, 70, 80, we're all the way up to here now. Here's our graph. We have the growth model and its graph. Let's continue further. Now that we have this population model, now that we have the doubling time model, what is the population going to be after 50 minutes? Yeah, 50 minutes is our argument. You're absolutely correct, Ryan. If we want to know the population after a time of 50 minutes, we can simply plug in this argument of 50, and we have something that we can put directly into our calculator. 10,000 times 2 to the 50 over 20. Well, let's get our calculators out and actually crunch those numbers in. 10,000 multiplied by 2 to the 50 over 20, and our population, 56,568.5, where are we going to round it? Because of course, if we're talking about bacteria, does it make sense to have 0.54 bacteria? That's the same idea. Does it make sense to have 0.54 people? Well, it's either a person or it's not. It's a bacteria or it's not. We know that this isn't going to be absolutely perfect, so where do we round it? Well, we have two different things that we can look at. Most of the time with our class, we've chosen to round to 3 significant digits. So if we round it to 3 significant digits, what would it be? 56,700. Accurate to 3 significant digits. Sometimes people will look at it and say, round it, just follow the standard rounding rules to the nearest whole. If we rounded it to the nearest whole, 56,569. One thing to keep in mind though, this is a process because we know the bacteria are splitting, we know that they're undergoing mitosis. Well, with this bacterial population growing under mitosis, this 0.54 is a representation that it's partially completed. At that exact moment when it hits 50 minutes, it has not yet finished a complete path of mitosis, a complete cycle. And so if it has not yet completed its cycle of mitosis, this part really shouldn't round upward because there's not going to be that many. Even though it's at 0.5, or even if it were at 0.9, the process isn't done, so it's not yet a whole bacteria. And so there is also a train of thought that says with these particular things, you would always round down no matter what. You would truncate and just cut it off and say, at the end, it doesn't matter what this decimal was, just leave it alone, 56,568. I'm pointing this out so that you can always pay attention to the context. For our class, we will round to 3 significant digits, typically. When you start looking at applied problems though, the point is, if you're going to do rounding, I request that you do one of two things. Either round to 3 significant digits following our standard convention, that's acceptable, or round downward. Because we don't have a whole amount, even though the 0.5 would tell us to round up, we won't do it because the process is not done yet. Pay attention to the actual physical constraints, the actual applications, and follow through with it. Also going to make a correction. A couple people noted, I just took a student's answer on this one and didn't even bother to look at it. It's not 56,700, it should have rounded to 56,600. I wasn't paying attention to the numbers and didn't catch it. So on this one, the population at time 50 is 56,568. Part of the thing we would want to consider with this, especially with science, how accurate are your measurements? For instance, did we start with exactly 10,000? Or was 10,000 already a rounded number? Was it actually 9,986? And it was rounded at the beginning at 10,000? Or was it a perfect 10,000? With the doubling time, is it actually 19.85 minutes, which was rounded to 20 minutes, or was it a perfect 20? Science will always have you look at significant digits based on measurements. In math, we will make the assumption every single number you're given is an exact value. We will always have in math the assumption that we started with an exact 10,000, not a rounded 10,000. It is exactly 20 minutes, not a rounded 20 minutes. And so we can go as far as we'd like with our significant digits. And now that your eyes have glazed over, let's ask this question. How long will it take for the population to triple? We'll come back to the model. If we started off with 10,000, what does it mean for the population to have tripled? Well, if we had an initial population of 10,000, and that population has tripled, what does that mean for us? It means the population at some point in the future is actually 30,000. So we need to determine what time t actually causes this to equal 30,000. Okay, so we can start by dividing by the... Man, this thing just does not like me right now. We can divide out by 10,000, giving us 3. Well, that makes sense, shouldn't it? 3 is tripling. And now we have this equation. What would you do to solve it? Absolutely, we'll have to take a logarithm. After taking a logarithm of both of them, we can apply the exponential rule, or the exponent, the power rule that we had, and note that the logarithm of 3 is equal to t over 20 multiplied by the logarithm of 2. Now what? We can do it in several different ways. I'm going to multiply by 20. And I'm going to divide to get rid of the logarithm of 2. And after both of those pieces cancel, we have 20 multiplied by the logarithm of 3 divided by the logarithm of 2. Then we have something that we can type into the calculator. So let's get to it. Using your calculators, what is 20 times the logarithm of 3 divided by the logarithm of 2? Times the logarithm of 3 divided by the logarithm of 2. 31.699250001. So where do we round it? 31.7 if we're rounding to 3 significant digits. So time is equal to 31.7 what? 31.7 puppies? Days, weeks, years, seconds, milliseconds. What was it? Since our original label on time was minutes, we'll stick with minutes. So it takes a little bit over half an hour. Continuing with our next example. A bacterial model doubles every 25 minutes. Its population is 3,000 at 4 p.m. How many bacteria will there be at 5:30? Where does everything fit? We know the population doubling time model. Where does everything go? P of 0 is going to be 3,000 because it's our initial population. So, okay, we're starting with 3,000.
The D is 25.
Okay, D is equal to 25.
And then T is 90.
Good observation. Good observation that we're starting with. Because we were using 4 p.m. as our starting point, of course, it's not like time has to start whenever. Time starts when we say it starts. And we chose to say time starts at 4. And so at 5:30, you're absolutely correct, Devin, 90 minutes have gone by, so our time, t, is 90. And so the population, 90 minutes after starting, that's what we want. 3,000 times 2 to the 90 over 25. Let's get our calculators out again and crunch the numbers. 3,000 multiplied by 2 to the 90 over 25. And our population, 36,377.1976. Where are we going to round it? Okay. If we want it accurate to the nearest whole number, we'll round it down and say 36,377. Verifying, yes, I remembered it correctly. So we're done. Let's progress further. Population is undergoing exponential growth. It grows 10% in 4 hours. What is the doubling time?
1.1.
Okay, so we can do several different things. P of t, P of 0, 2 to the t over d, and let's start putting pieces in. Devin, you quickly told me 1.1. Okay, 1.1, an increase, if it has grown 10%, that means it is a 10% increase. The original amount was 1, and 10% more is 1.1. Sometimes when we're working with percents like this, some students get confused by it. One other component you can do, if this stuff that I just said doesn't make sense, make up an initial population. They didn't tell us how many were there originally. So let's just say originally it was 100. At some point in the future, if there has grown 10%, that would tell you there are 110 in the future. Sometimes students will prefer this piece in the red. What is the time? 4 hours. I'm pointing out that both of these things that we're doing, both the red and the blue, are valid ways to set it up. In the blue, I recognize that I started with 100% for the original amount, P of 0. And then when 100% grows, that becomes the decimal 1.1. Some students get confused by the piece in the blue, so you can make up an initial population size and use the red instead. It's valid because when you go through and solve it, your first step is to divide out by the initial population. What do you notice? You create the same thing that's in the blue anyway. So if you want to make up an initial population and just say, I'm using the fake number, you're going to wind up getting the same result. So it really doesn't matter. I'll let you know my preference is I prefer the stuff in percents. I prefer the blue. That's why we spent so much time doing percents earlier, so that we wouldn't have to do the stuff in the red. Anyhow, now that we've reached this stage, what's next? I don't need the times 1, because multiplying by 1 keeps things the same. To get an exponent, we need logarithms. So we have the logarithm of 1.1 equals 4 over d times the logarithm of 2. And now what? I'm going to choose to multiply by d, which gives me d times the logarithm of 1.1 equals 4 times the logarithm of 2. And to get rid of then this multiplication, divide. Dividing by the log of 1.1, we get precisely what we needed to put into the calculator. D is equal to the log. D is equal to 4 times the log of 2 divided by the log of 1.1. Use your calculator and tell me what those are. Taking your result, Devin, what is it?
29.09016.
29.0916, and we'll stop there. Rounding to 3 significant digits, what is its doubling time? I apparently left out a 0, that's going to be inconsequential because rounding to 3 significant digits, we get 29.1 hours. Please notice, each one of those pieces we were doing were based on how long does it take for the population to double. Of course, that's why we call it the doubling time model. Very similar to it, we have the half-life model, in which case we're building it not based on doubling with a base of 2. We'll use a base of 1/2 to see repeatedly half times half times half times half, in which case we wind up with virtually the same kind of a graph, where we have half, 2 times the half-life, 3 times the half-life, 4 times the half-life, 5 times the half-life. And if we start at the top with our initial amount, the initial population, well, at a time of 1, it gets cut in half. And so here we would have the population at time of half-life. At 2 half-lives, it gets cut in half again, and cut in half again, and cut in half again, and cut in half again. Each time, half and half and half and half. Well, if you keep cutting things in half over and over and over, you're going to get closer and closer to having nothing. The model, please note, is virtually identical. Instead of having t over d, it's just t over h. Using a dummy variable, we could have used p instead of a for an amount. The only difference is the fact that we're using 1/2 instead of 2. Graphically, it looks like this. Pause the video, write it down, and now we'll move on. The half-life of carbon-14, which is used to radioactivate basically all organic matter. It has a half-life of 5,730 years. Here's the half-life model and its graph. Well, once again, let's run through and plug things in. What goes where? What is a of 0 in this problem? What is the initial value? We're not told a number for the initial value. You would have to recognize the initial value is 100% of something. We don't know the number. 0.100%, and that 100% is just the number 1. Continuing further, we were told the half-life is 5,730. And so here is our half-life model. Whatever this original amount was, we don't know, but it was the initial population amount. Creating our graph, 5,730 years is the half-life. And so if we double that, we get 11,460. And if we triple that half-life, 17,290. 17,190. And we'll start up at the top for our initial population. At a time of 1, it got cut in half. At a time of 2 half-lives, it got cut in half again. At a time of 3 half-lives, it's cut in half again. And so we can follow the pattern and note it will wind up having a horizontal asymptote. And there's our graph. Let's use the model. If that initial amount was actually 0.025 grams, how many grams will remain after 11,460 years? Well, we can actually put things into the model. The amount after 11,460 years, the initial amount multiplied by half, 11,460 divided by the half-life, 5,730. Well, basically, what we should recognize, that was 2 half-lives. 2 times 5730. So all this is doing, taking the original amount and applying the half-life twice. So what is half of 0.025? And we're done. After 11,460 years, there would have to be 0.0625 grams. Which frankly isn't a whole lot when you consider a paper clip weighs about 1 gram. Or has mass of a gram. Grams are actually not measurements of weight, they're mass. Let's continue this further. Half-life of a substance is 5,730 years, and 2,000 years later, we have the remaining amount. How much did it have to begin with? Let's start putting in the information we know. The half-life is 5,730 years. The amount remaining was the value we had at some point after 2,000 years. We're trying to figure out the initial population based on the time of 2,000. So solve this equation, and we will have our value. How do we solve it? although it looks complicated, this is just a number. We can put that into our calculator and get a number like, I don't know what it is, 5 or 3 or 0.02 or whatever number it comes out to be. But that's a number. So to get the a by itself, we can divide by that blob of stuff. And so we get exactly what we want to type into the calculator. 0.00054 divided by this blob of 1/2 to the exponent, and we'll get our result. So let's run over to the calculator then. 0.00054 divided by, parentheses for 1/2 to the exponent of 2,000 divided by 5730. And noting that we have e to the -4, we would have then 0.1236878. If we were to round this to 3 significant digits, the 8 would tell us to round upwards on the 7. And we have our solution. The half-life of the radioactive element Einsteinium, yes, it was named after the Einstein, is 20.47 days. How long will it take Einsteinium to decay so that there is only 1/1000th of the original? Okay, so in the future, 1/1000th remains, based on the original amount of 1. Our half-life is 20.47 days, and so we've built the model. Solving it, we would have, we'll take the logarithm of 0.001 times then t over 20.47 times the log of 1/2. The log of 0.001, 10 to what power gives you 1/1000? So we recognize that this whole piece right here is just the number -3. So when we multiply by 20.47 to cancel, and we divide by this logarithm, we get something we can type into our calculator and get the value. I see you're already typing it in, Ryan. What did you get? And we'll stop there. So rounding to 3 significant digits, frankly, even if we were to round to 6 significant digits, we'd wind up with 204 days. And then our last example for this video, beryllium-14 undergoes rapid radioactive decay. Only 0.0570 of the original amount remains after 20 seconds. So what is its half-life? Okay, the original, we have the amount in the future based on the original amount of 1 with a half-life then of h. That's what we're looking for. And our time in the future was 20 seconds. So once again, we've built the model, and we'll use our exponential and logarithmic ideas, our formulas and processes to get the solution. We have the logarithm of 0.0570 equals 20 over h multiplied by the logarithm of 1/2, ultimately telling us that h is equal to 20 multiplied by the logarithm of 1/2 divided by the logarithm of 0.0570. And after putting those in the calculator, we get 24.66. Rounding it to 3 significant digits, the half-life is 24.7. And I'm looking at this and thinking that's not correct. I know that this time is not correct. And going back to my calculator, I forgot to type in the 0. In the calculator, I typed in 0.57. I forgot to put the 0.057. After typing that back in and fixing it, I get 4.839, which when rounded to 3 significant digits, actually gives us 4.84 seconds for the half-life of beryllium-14. Noting back where this led us. Yes, it was a particularly long video, a lot of material included. However, please notice the main features we had, base 2 and base e as exponential models, are very, very similar to each other. Even the doubling time model and the half-life model are very, very similar to each other because they are both exponentials. The only difference, however, is a doubling time uses a base of 2, the half-life uses a base of 1/2, and outside that, I build the model and then use the topics from 5.1 to actually solve.